Dear students, today we will start next part of the oscillators, that is LC oscillators. And in LC oscillators we have three main types: Hartley, Colbert and Clark. You can say we will discuss one by one all these three. So first one is the Hartley, second one is the Colbert's, and third one is the Clark. In LC oscillator, feedback network. In feedback, we use LC circuits. So first we will take Hartley oscillator. In Hartley oscillator, feedback network is a combination of two inductors and one capacitor. And in Colbert, we have two capacitors, one inductor. So first of all, we will draw the circuit, basic circuit of the Hartley oscillator. In Hartley oscillator, suppose we are using transistor as a basic amplifier. So common emitter configuration. So biasing, suppose we are using potential divider bias. Here we have capacitors. So here we will use a choke. This is called the radio frequency choke. And capacitors are present for coupling. At base, suppose we are using CV. As collector, at collector, suppose we are using CC. And at emitter, this is C. You can assume any value, suppose R1, R2 and RE are resistances. So this is the circuit for basic amplifier. And feedback network, which is joint between input and output. This is the output and this is the input. This is the input and this is the output. And between input and output, we have a combination of two inductors and one capacitor. Here L1, L2 and C. This is grounded and this is connected to ground. Emitter is connected to ground through this loop, resistance and capacitance. So what happens? So in short, you can see working of this Hartley oscillator. What happens when we bias this transistor? This AC transient current, AC current, or you can say transient current. Transient current is established in this inductor because this current is a variable. Current cannot change instantaneously through inductors. And due to coupling of these two inductors, so these two inductors act as auto transformer. There is a voltage induced in this and there is a 180 degree phase shift. So here we have a AC voltage introduced through charging and discharging. When current established, this is charged, and once through capacitor this is charges, again this charges through inductor and then discharging. So oscillatory current, main thing is this oscillatory current or voltage is established through this tank circuit. This is called feedback network, or this is also called tank circuit. This purpose of this tank circuit is to establish a oscillatory voltage or current, and due to auto transformer action, this is connected to output. So feedback is established between output and input through this network. So now we can find out frequency of oscillation for this oscillator circuit. What is frequency of oscillation for this Hartley oscillator using transistor? So next we will write frequency of oscillation. Frequency of oscillation for Hartley oscillator. So first we will draw AC equivalent circuit. AC equivalent circuit. So now for AC equivalent circuit, so see here, this is the transistor. This is the transistor, and these are three terminals: collector, base, emitter. And for AC analysis, capacitors are shorted. So this is grounded. Emitter is grounded. And what happens here? This, we are taking an equivalent resistance here, R, and feedback network, which is combination of two inductors and one capacitor, L1, L2 and C. So this is the tank circuit. This is connected to input, L1, L2 and C. Obviously this is a variable resistor. We can vary frequency through this. And this is connected to this ground. This between L1 and L2 we have ground terminal. So this is connected to ground. And what is R here? This is the combination of, actually this is the combination of three resistances. One is resistive effect of inductors, or you can say losses, plus output resistance of transistor, plus you can say load. So this, for simplification, we are taking only one resistance here. Actually this is the combination of three parts. In resistive part of this inductor is included here, and output resistance of transistor, when transistor is modeled, we have an output resistance for that transistor. This is also included in this part. And load, any load available, capital RL or anything which is present in the circuit, that is included in this part. So this is a combination of resistances. Now from this circuit we will derive frequency of oscillation. One more equivalent circuit is required here. So now we will replace this transistor by its hybrid pi model, and then from that circuit we will find out the frequency of. So this is the, you can say this is the AC equivalent. And here for another circuit which is used, first we are using, this is grounded, this is base, emitter, collector, and collector is voltage dependent current source, GMV5. Basically this is the V5 and this is the grounded. Now see how all these elements are connected in this. And this is in between collector and emitter. This R is connected. So this is emitter. You can collect here one resistance is connected between. This is connected between collector and emitter. Inductor L1 is connected between collector and emitter, and another inductor is connected between base and emitter. So one inductor is here between collector and emitter. So this is the L1 which is connected between collector and emitter. This one. And this part, this is connected between base and emitter. So you can see this is base and emitter. Another inductor is connected here, L2. Base and emitter. Emitter is grounded. And what about this capacitor? Capacitor is connected between collector and emitter. So you can connect this capacitor here in between. So this is the variable capacitor between collector and emitter. So this is the final AC equivalent circuit using model, transistor model. So this is the equivalent circuit, and from this is the final circuit, and from this we will find out the frequency of oscillation. Now apply KCL at the output node. Now from this frequency of oscillation, you can say derivation. This is the derivation of frequency of oscillation. Apply KCL at the output node. So applying KCL at output node. So this is the output voltage. Suppose here we are taking V0 as output voltage. So we have 1, 2, 3 and 4 branches at this node. 1 current, 2 current, 3 current and 4 current. So we have 4 parts. So after applying KCL, we can write like this. This is the current through L1 plus voltage upon impedance. Then voltage through resistor. This is the current through resistor plus dependent voltage source. This is the current And next part is current through this. Current through this part. So we have four parts. This is the current through inductor, current through resistor. One, this is voltage. And this is the current source. And another part is this one. So total impedance in this is combination of these two, L2 and C. So we can write V naught upon total drop is V naught. V naught means this is drop between output node C and emitter which is grounded. So this is the total drop, and this drop is combination of two drops, drop across C and drop across L2. So now you can write this is as L2 plus 1 upon S equals 0. Algebraic sum of currents equals 0. So this is the, now see what is this V pi. We can also write this voltage V pi in terms of V naught. How? This is the total drop across C and drop across L2, and V pi is the drop only across L2. So we can apply potential divider here for this. So V pi you can write, this is the drop across L2. So you can write SL2 upon SL2 plus 1 upon SC into V naught. This is the potential divider. Now you can replace, and after replacing you can write V naught upon SL1 plus V naught upon R plus GM SL2 upon SL2 plus 1 upon SC into V naught plus V naught SL2 plus 1 upon SC equals 0. Simply replacing value of P pi. So now from this one we will proceed for derivation of frequency of oscillation. So this is the expression. Now you can take V naught common because all terms have V naught. You can take this common and you can collect terms for simplification. You can also take LCM because these two terms are same as L2 plus 1 upon SC. So if we take here LCM, then LCM for all terms is this SL2 plus 1 upon SC. This is LCM, and here you can write 1 upon SL1 plus 1 upon R into this term SL2 plus 1 upon SC plus this is simply GM SL2 and this is 1. So equals 0. And from here when this is multiplied becomes 0. We have only all these terms in numerator. When we will collect this term, you can write V naught square term. First is square term. This is square L 2C. You can see all terms are rotated here. Plus C plus S square L2C plus 1 into 1 upon SL1 plus 1 upon R equals 0. So SL1 upon R, you can see here, you can take LCM here. So then this will become S square L2C here. S square into C plus 1 upon SC, and when this SC is multiplied by these terms, you will get this S square into CGM plus SC. So you can take here SC as LCM. Now you can separate terms. Since V0 is not equal to 0, therefore another factor is 0. So you can collect terms. First, L2C plus SC plus 1 upon SL1 plus 1 upon R plus L2C upon L1 plus S square L2C upon R equals 0. After separating all terms, you can multiply and expand all these terms. Now, first quadratic term. So, these terms contain S square. These terms, there are two terms containing S square. So, you can separate these two terms and you have GM L2C plus from here L2C upon R. Then term containing this factor. What are terms? Here this term contains, this term contains, and you can take as common. Here you will get S square in denominator. You can collect all these three terms. You can take common and you can write here C plus from there this is L2C upon L1 plus from here you have 1 upon S square L plus a constant term is, this is the constant 1 upon R equal to. So after collecting three groups, this is the one group, this is another group, and this is the third one, the constant. Now to find out the frequency of oscillation, you can replace this value. Put S equals j omega. Obviously, S square equals minus omega square. So from here, you can write this is minus omega square, first term, all these terms, Gm L2C plus L2C upon R plus you can write constant term, then imaginary part from here. Imaginary part, this will give you imaginary part, this term only. This term will give you imaginary part because this is real and this is also real. So from here you have this will become omega square. So in bracket all three terms are real. Outside this is j omega. So this is C plus L2 upon L1 C plus this S square, that is minus 1 upon omega square L1. So yes, you can find out frequency of oscillation. After putting this value S equals j omega, this is the expression, and this is equal to 0. So obviously imaginary part is 0 and real part is 0. This is whole is 0 means you can separate x plus dy. Means real part is also 0, imaginary part is also 0. Then from this you can write omega c L2 upon L1 into c minus 1 upon omega square L1. This is 0. This is from, if we replace imaginary part 0, then this is expression. And from here we can calculate frequency of all. Since omega is not 0, therefore c plus L2 upon L1 c minus omega square L1 equals 0. And this implies 1 upon omega square L1. This is equal to c plus L2 upon L1 into c. Okay, you can take this common. C is common. 1 plus L2 upon L1. So from here, after placing this value, 1 upon omega square equals you can take this LCM L1 plus L2 upon L1, and this L1 is cancelled out. So 1 upon omega square equals C into L1 plus L2. Or if suppose assume this two inductors is given by an equivalent, then you can write 1 upon omega square equals CL equivalent. And from here you can find out omega equals 1 upon under root CL equivalent, or 1 upon under root C L1 plus L2. So from here you can also write frequency of oscillation is given by 1 upon 2 pi under root C L equivalent. So this is the expression for frequency of oscillation for Hartley oscillator, where L equivalent is given by this expression. L equivalent is simply combination of series combination of two inductors L1 L2. So this is the procedure to derive frequency of oscillation for Hartley oscillator. And now we can find out condition also. This is the, when we will put real part equal to 0, we are putting only imaginary part is equal to 0, then we are getting this frequencies, and then we will put condition. So this is the frequency of oscillation which is required. Now condition for oscillation. This is obtained from real part. Real part, when we put this real part equal to 0, then it means minus omega square Gm L2C plus L2C upon R equals 0. So this is the real part, and we can calculate condition on this part. This is the final frequency of oscillation. When we replace this value of omega square, so you can write here condition is one thing is missing, I think. That is the, in real part we have 1 upon r also. So from here omega square Vm L2C plus L2C upon r, this is equal to 1 upon r. You can take this whole term in one side and this term in one side. You will get, and you can put this value of omega square. What is value of omega square? This is 1 upon C L equivalent. That is 1 upon C L1 plus L2. You can put this value. And after replacing this value of omega square, you can write here, this is 1 upon L equivalent C into Vm L2C R plus L2C equals 1. You can multiply by R. So when you will multiply by R, this is the expression. And from here you can calculate. So C is cancelled out and L equivalent is, now expression is Gm L2C R plus L2, okay, equals what? L1 plus L2, or this is Gm L2R equals L1, and from here this is L1 upon L2, this is given by Gm. So this is the condition. This is called condition. L1 upon L2, this must be equal to Gm. So this is all about Hartley oscillator, frequency of oscillation and condition for oscillation. So first we will draw equivalent circuit from circuit of the oscillator, and we will replace model for transistor. Then we will apply KCL at the output loop, and after application of KCL we will solve for frequency of oscillation and for condition. So this is all about for today. Okay, thank you.